Hello, today we are going to be going over how to solve a combined spectra problem. So the information that we're going to be given is the molecular formula, the IR spectra, the 13 carbon NMR spectra, and the proton NMR spectra. The first step we're going to do is calculate the degree of unsaturation. So here's our given molecular formula, C6H12O2. And here is the formula to calculate the degree of unsaturation. The C represents the number of carbons. This N represents the number of nitrogen, which as you can see, we don't have any. This X represents the number of halogens. Once again, we don't have any. And then hydrogen, the H is for hydrogen. Okay, so let's calculate this. We have 2 times 6 plus 2 minus 12. All of this is going to be over 2. So 2 times 6, right here we have 12, plus 2 is 14, minus 12 is 2. All of that over 2 is 2 over 2, which is equal to 1. A degree of unsaturation of 1 basically just means that our molecule either has a ring of some kind or one double bond. So let's dig a little deeper to try to figure that out. Okay, so next we are going to determine the number of unique carbons and hydrogens from the spectra that's given. So we'll start here with our carbons. We are just going to count the number of chemical shifts, and that will tell us how many unique carbons. So we have 1, 2, 3, 4, and then there's 2 kind of here together. You can see they end at different spots. So 5, 6. So we have 6 unique carbons. Next, we're going to determine the number of hydrogens, and this is our proton NMR spectra. We're going to do the same thing, just count the number of peaks here. So we have 1, 2, 3, 4, 5. So 5 unique hydrogens. The next step is to identify the diagnostic functional group in the carbon NMR spectra. So that we're going to be looking at this one right here. I would say this is about 175-ish. And looking at charts, you can conclude that in the range of 165 to 185 is going to be a carbonyl group, which going with our molecular formula is either going to be an ester or a carboxylic acid. This obviously makes sense with our molecular formula having 2 oxygens in it. The next step, we're going to evaluate the potential functional groups and eliminate the group that does not fit the data. So for a carboxylic acid, we would be expecting a peak around this area. Actually, it'd be a little higher than that, more like up here. It'd be, you should have a shift for carboxylic acid at 10.5 to 13.0. And this is basically just representing the hydrogen that would be bonded to the oxygen in the carboxylic acid group, which we don't have. So we can conclude that this molecule is going to have an ester functional group within it. The next step is to examine the spectra, consider the chemical shifts, splitting patterns, and integration to determine fragments of the molecule. So we're going to start off with our proton NMR and just analyze each chemical shift. So our first one is at about 4.2. You can see right here that it is representing 2 hydrogens. There are 4 peaks, which means it is a quartet. This means that it is on a carbon that is adjacent to carbons that contain 3 hydrogens bonded to it. And because it is shifted a little bit more downfield, we can deduce that it's also bonded to the oxygen that is in the ester. Our next chemical shift is at 2.3, this one right here. It also represents two hydrogens. It is a triplet, and so we can deduce that it has two hydrogens on adjacent carbons. It's also a little bit more downfield than our alkyl groups. So we can also deduce that this one is bonded to the carbon that is bonded to both oxygens in the ester group. The next chemical shift is at 1.7. This is also representing two hydrogens. It is a sextet, so there's six peaks here, which means that it is on a carbon that's adjacent to carbons that contain five hydrogens. So this is the fragment piece that we can deduce from that. It is attached to the methyl group and then this CH2 as well. The next one is at 1.2. This one represents three hydrogens, and it is a triplet. So it is bonded to a carbon that has two hydrogens. You can see it is representing the methyl group, and same for the next chemical shift, which is at 1.9. Also representing three hydrogens. Same thing, it's a triplet. So it's adjacent to a carbon with two hydrogens. These are both the methyl groups on the terminal ends of the molecule. Next, we're going to move on to the carbon NMR spectra. So this chemical shift right here, kind of like what we talked about earlier, is at 175. This is an sp2 hybridized carbon. It is the carbon that is double bonded to an oxygen and also single bonded to a carbon and another oxygen. And then these chemical shifts down, or I guess it should be upfield, are all sp3 carbon or hybridized carbons, and their shift downfield just depends on their proximity to the functional group. And now finally looking at our IR spectra, we can see this peak here at the 3000 frequency. This is representing our carbon hydrogen stretch. This is our main diagnostic, This is our main diagnostic peak right here. This is our carbon oxygen double bond stretch here at 1750. And then these in the fingerprint region at 1200 are representative of a carbon oxygen stretch that's also in the ester group. So based on all this data, our proposed structure is this right here. We have ethyl butyrate. This makes sense. We said we had six unique carbons. So that's 1, 2, 3, 4, 5, 6. And all of these have unique hydrogens except for this one, which would make sense why we have 5 unique hydrogens. I think that's it. Thank you.